Hello everyone, this is Andrew Moscovich, and I'm going to be presenting on my investigation of the Dickerson power plant's contribution to potential arsenic surface water MCL exceedances. So without going into great detail about the project background, since we're all familiar with the project description, um, here's a simple diagram. And essentially what's going on is we have the Dickerson power plant, which combusts coal, and arsenic is a component of coal. So when combustion takes place, some level of arsenic is emitted through the stack and released into the atmosphere, and that arsenic will eventually settle onto the ground or surface water and potentially migrate to the Potomac River. Um, a great deal of the particulate matter is filtered out at Dickerson by baghouses, and therefore a lot of the arsenic doesn't actually get released through the stack. Uh, as also, fly ash remains. It's a byproduct of combustion, and so that fly ash needs to be stored somewhere. And Dickerson stores it off-site in pits that are depicted by the blue rectangles in the bottom right. And during precipitation events, leaching can occur, and that arsenic can infiltrate the groundwater and potentially move downwards in gradient towards the Potomac River. The Potomac River has a background concentration of arsenic, as well as the tributaries that come into the Potomac River. Within our modeling domain, we also have wastewater treatment plants that are releasing arsenic into um, the Potomac River. And we have points of extraction, and these are our primary points of concern. Uh, we want to understand what the concentrations at those extraction points are going to be, especially if they're for drinking water utilities. And we want to make sure that they don't exceed the arsenic MCL, which is 10 micrograms per liter. And further, we're aiming to understand how the Dickerson power plant contributes to the concentrations of those intakes. To better understand if MCLs for arsenic might be exceeded because of the Dickerson power plant, I've built three different models, uh, one for each environmental domain, and those domains being air, surface water, and groundwater. And in each of those models, we've modeled the fate and transport of arsenic. And so this presentation is going to be going over each one of those models in detail. So we'll start with my air model and we'll go over the calculations that went into the model. So I started with a logic diagram that's in the center of the slide. Uh, the first question is, what is your buoyancy factor relative to 55? So I used the equation just to the right of the logic diagram to calculate buoyancy factor, and I got 254. And so the answer here was my buoyancy factor is greater than 55, and so I proceeded down to calculate my F factor, which I got a value of 1.09 kilometers. And so I proceeded further down the logic diagram, and it asks, is the stability E or F? And we were told to assume slightly unstable conditions, and that correlates with a stability class of C. Therefore, the answer here is no. And so I proceeded further down the logic diagram to the question, is X less than XF? And I set up my grid cells to be to go from 2 kilometers to 40 kilometers downwind. And so since my XF was 1.09 kilometers, the answer here is no. X is not less than X of F. And that led me to the Plume-Rise equation that I had to use. And I won't go into the Plume-Rise equation in much detail, but something that Dr. Robert emphasized was here you're supposed to use the wind speed at the stack height. And so I used the equation to the left of the logic diagram to correct the given wind speed, and I used the correction factor associated with the stability class C and a rule setting. From here, I calculated dispersion in the y and z directions, and I did that with the sy and sc equations shown on the bottom right. And here you just want to make sure that you are using the right coefficients from the right stability class, and that's why I have them boxed. From here, I was just about ready to calculate concentrations with the Gaussian plume equation. Notice that this form of the Gaussian plume equation in the bottom left has been simplified. I'm interested in the concentrations at the ground level. Therefore, we set z to 0. Um, some inputs that I had to calculate beforehand was the h value here is of the plume centerline elevation, and so you had to add the plume rise to the stack height, and then you also had to correct your wind speed to the plume centerline as well. And then in regards to emission rate, we were given the annual heat input of the Dickerson plant, and we were given a regulatory limit for particulate matter emissions in units of uh, MMBTUs per, sorry, in units of pounds per MMBTUs. And so by doing a little bit of algebra and assuming that all of those heat input times they were operating at their regulatory limit, you could come to an emission rate. And you'll see in the next slide that I have results for PM and for arsenic. So for arsenic, you would just take this value, this PM emission rate, and multiply it by the 50 ppm that we were given in the guidance document. Here are the results of all of my computations. Uh, this was the product of the final Gaussian plume equation that we went over. Uh, so one of the things you could easily recognize is that there's a Gaussian shape to my data, which is good. It's what you would expect. Um, and then as the arsenic and particulate matter disperse, uh, you get a ever more decreased concentration of PM or arsenic, whichever one you're looking at. And I don't want to interpret this data too much because the goal is to determine if surface water MCLs are exceeded, but we're going to use these concentrations that we calculated at a ground level along with the settling velocity to calculate a flux to help us understand the impacts to the potential impacts to the surface water concentrations of arsenic. One of the questions we were asked to answer was how does the Dickerson power plant compare to the other power plants in the region in regards to the particulate matter it emits. And so I used this map on the right from the Wang study that Dr. Robert provided us with. And if you looked at the map on the left, there's some indication of the modeling domain from the Dickerson power plant to the DC area, which is around 40 kilometers. And so when I compare the two maps, it looks like where we have a PM 2.5 concentration between 0.5 and 0.8 micrograms per meter cubed, and those concentrations are due to 5 different power plants in the region. And so when you compare that with uh, the concentrations that I calculated and showed you guys in the previous slides, to me, it appears that Dickerson is definitely a significant emitter of PM 2.5. The other plants do contribute to the PM concentrations. It's not solely Dickerson, but Dickerson surely is a significant factor. One of the things I was curious about was given the rise of natural gas use in energy production, I was curious to see if Dickerson was basically the sole contributor of PM uh, in this data set, because if the other 4 plants were, say, natural gas fired plants don't emit anywhere as much particulate matter. But it doesn't appear to be the case. I suspect that at least one or two of these other power plants are also combusting coal. So here I've calculated mass load of arsenic from the air to the ground or surface water. And I did this by using the equation shown. I took the arsenic concentration that I calculated from the Gaussian plume equation and multiplied it by the settling velocity, which I'll go over in the next slide, and then multiplied it by that grid cell's area, which is 4,000 square meters for each grid, and then just corrected for time. And so if you look at the data, the orange columns indicate the largest loads, and it seems that the largest arsenic load is around 2,000 micrograms per day. And the reason I point that out is so that when you look at the surface water loads that I'll show, that you have a sense of, well, is this load from the air to the ground or surface water significant? And you'll find that it's not. 2,000 micrograms per day depositing on the ground or surface water is pretty small relative to, say, the Pepco effluent or even just the arsenic that's deposited into the modeling domain or the Potomac River from its tributaries. We were given a particle size distribution for the particulate matter emitted from the Dickerson stack, and I used that to calculate weighted settling velocities for each range. And then in my calculations from the previous slide to calculate mass load and flux, I used the weighted average settling velocity. I could have been conservative and just used the maximum weighted settling velocity, but rather I just used the average and I performed a sensitivity analysis, which I'll go over later on the settling velocities. And so you'll see in my table that, or you could look either at the table or the chart, the upper right chart, that our smallest particles, 0 to 0.1 micrometers, have a settling time of around 25 or 24,000 days, and that's a really long time. But in actuality, if you look at the bottom graph and the marks on it, those small particles over time, as they travel, are going to coagulate and start forming larger particles. On the other end of the spectrum, the coarse particles are going to settle out, and if you look at the table, you'll see, say for the particle size range 1 to 2.5 or 2.5 to 10, that the settling time I calculated was, 20 to 1.5 days. And so those are the kind of particles that you could expect to settle out rather quickly. And so this plume of particulate matter, if you will, is going to change over time. The smaller particles are going to coagulate, form bigger particles. A great deal of the particles will be stable and they will stay afloat for a significant amount of time. And then the coarser particles are going to settle out rather quickly. We were asked to consider secondary particulate matter emissions. It takes about a day to form sulfate aerosol, which is secondary particulate matter, from sulfur dioxide, which is the primary particulate matter emitted from Dickerson. Our modeling domain extends 40 kilometers downwind, and the wind speed at the plume centerline is 5.8 meters per second. So by doing just some simple algebra shown, it takes the particulate matter only around 2 hours to leave the modeling domain. And so what that means, given how long it takes for secondary particulate matter, well, at least sulfate aerosol to form, what it means is that we don't really have to consider it in this case. Secondary particulate matter can certainly be significant and should be considered, but given the size of our modeling domain and our wind speed and our plume centerline, it's not something that we have to consider. Here is my mass balance on arsenic. To do this, I had to make some assumptions. I referenced some EPA air quality monitors to determine a reasonable background concentration, which seemed to be 10 micrograms per meter cubed. And then I had to convert that concentration to a mass load. And so I used the velocity at the plume centerline, even though obviously the velocity ranges from the ground level wind speed all the way to the plume centerline. Uh, for the y direction in my area, I used 60,000 because that was the y length in our modeling domain, and then I used the plume centerline height. And I also assumed that the PM 2.5 that's in the background has a similar composition of arsenic, so it was 50 parts per million arsenic, just like the Dickerson PM was. Um, and then, the arsenic emitted, I was able to easily calculate with the data that I've already shown, as well as the arsenic that fluxed to the ground. One of the things that I had to make assumptions for was, or more assumptions for, was the arsenic captured by the baghouses. Uh, what I did for that was I assumed that uh, the baghouses were operating at 99.98 efficiency, something among those lines that the project guidance indicated. And so I essentially back calculated from how much arsenic was emitted, I back calculated how much arsenic was prevented from being emitted from the baghouses. And so if you look at the bottom right, there's my mass balance. I didn't assume that any of the background arsenic settled in the modeling domain, just because I was curious what the data would look like from actual stack emissions. Um, so I have 0.11 kilograms per day of arsenic being emitted from the stack. Uh, 2.1 to the times 10 to the negative 5 uh, kilograms per day of that arsenic being emitted is fluxing to the ground or the river. So that's a really small amount of the total arsenic emitted. And the remainder of the arsenic is transported across uh, the boundary domain. And then 55.7 kilograms per day of arsenic is transported from the power plant to the storage pits. And that's why I wanted to include the arsenic captured in this mass balance, because it really displays how much arsenic uh, is moved to the storage pits rather than emitted through the stack. I performed my sensitivity analysis on the settling velocity. Uh, I used basically the maximum potential settling velocity, assuming all the particles were the biggest size in the given range, uh, and then also used the settling velocity for the smallest particles in the given range, and then in the middle I used my average weighted settling velocity. And you can see by looking at the results that there is a pretty significant difference if you look at these different settling velocities. The magnitude of arsenic load from the air to the uh, ground is a lot more significant with quicker settling velocity. And so if you look at the data cell by cell, uh, or grid by grid, if you will, in the orange uh, highlighted cells, even in the cells with the maximum settling velocity, they're still pretty insignificant relative to the amount of arsenic load you get from, say, the Pepco wastewater or just from the tributaries. But if you do add all of these cells up, it does add up to be a significant amount of arsenic that does have the potential to uh, alter the concentration of the surface water. Um, and so what we're going to be doing next is taking a look at surface water to see what those concentrations look like without considering uh, any arsenic from the air depositing. So now we're on my surface water model. To the left is a picture from Dr. Stoddard's lecture materials that uh, just displays the surface water modeling domain. And then to the right is a table of mine. The blue highlights indicate either the upper Potomac or the tributaries. The red indicate the intakes, which are the points of uh, primary concern. And then the browns indicate wastewater treatment plants or PEPCO effluent. Something else worth mentioning on this slide is if you look at the far right columns, the two far right columns, you'll see the concentrations for total suspended solids and arsenic that I used. And for the upper Potomac as well as the tributaries, I used the site-specific data uh, from the various studies that I have referenced below the table. I opted to use a non-conservative plug flow model. Uh, the reason I opted to do it non-conservatively is because arsenic does absorb to total suspended solids, and the fraction of particulates indicated that arsenic was neither a weak or strong sorber, um, based off of the Chapara study we were provided. And so if arsenic had it been a weak sorber, I perhaps would have used a conservative model, but that wasn't the case, so I went with non-conservative. In regards to the plug flow aspect of the model, I decided to go with that because we're dealing with a free-flowing river dominated by advection, and there's no longitudinal mixing. Uh, I'm not going to narrate my calculations as I did for the air model for the sake of time, but I do have some equations pasted here, and I'll go over some of the assumptions in case uh, you're looking at my data and finding that it looks different than yours. So for one, for total suspended solids, I didn't assume any settling. I just did a mass balance of the total suspended solids throughout the modeling domain. For the fraction of particulates, I use a mean KD value from the literature we were provided. Uh, and then for the settling velocities, I assumed that 50% of the particles were silt and 50% of the particles were clay. And then I took the average of the settling velocity, the median settling velocities for each of those particles. This figure displays the results of my non-conservative plug flow model. The red dots indicate the various concentrations at the various intakes. The blue are the concentrations in the Potomac at certain river miles. And the orange line is a reference point to the 10 micrograms per liter MCL. And so if you look at the data, one of the things you'll see is that the we're seldomly exceeding 1 microgram per liter of arsenic, and that's good. That means that we're well below uh, the MCL, at least considering strictly surface water sources. This slide shows the results of my arsenic mass balance in surface water. One of the things that I had to compute was the settling loss, and I did this by summing the mass of arsenic from the upstream inflow, the tributaries, the wastewater treatment plants, and the PEPCO effluent. And then I subtracted from that the mass of arsenic being removed from the water intakes, the downstream outflow, and the PEPCO intake. And so you can look at the chart on the left, that's the numerical loads, uh, and then the pie chart on the right just displays the percentage is of loads. And so if you look at the orange, it's pretty evident that settling loss from arsenic is really significant in my model. 31% of arsenic is settling to the river bottom at any point in time. 23%, the light blue, is showing the mass that is entering the modeling domain from tributaries, and so that's pretty significant. 23%, given my assumptions for background concentrations, is coming from the tributaries. And then another thing I'll point out is the yellow, the 14% block, is showing the PEPCO effluent, and so quite a significant amount of arsenic is uh, coming to the Potomac River from the Pepco's effluent. So the first sensitivity analysis I performed on my surface water model was on the background concentrations of arsenic. So like I said, I used in my model uh, the site-specific arsenic concentrations, and when there was no site-specific concentrations for a tributary, I just took the average of all of them and used that. Uh, but here I varied the arsenic concentration all the way up to 9 micrograms per liter for the tributaries and the upper Potomac. Uh, and all the literature indicated that that was kind of the upper range of arsenic that you would observe. And then I used the lower range that the literature we were provided with indicated was possible, which was a concentration of 0 micrograms per liter. Um, you'll see that the closest we ever get to the MCL is at the River Mile 195, which is the upper Potomac, and that's just because we assumed that the concentration was already at 9 micrograms per liter. But once we have the wastewater treatment plant effluents and other effluents coming into the system, the concentration quickly gets diluted. And so even at the upper boundary, exceeding the MCL of arsenic is unlikely. I also performed a sensitivity analysis on the settling velocities. Uh, I took the shortest settling velocity from the clay particle size range, and then I took the longest settling velocity from the silt particle range. And then I graphed that along with the median, the averaged median settling velocity that I used in my calculations. And what you'll see here is when we're at the lower settling velocity, the concentration can get as high as 1.8 micrograms per liter. So that's not extraordinarily higher than what we observed with the average median data, but it definitely is higher. And then when we assume that all of the particles are clay, uh, we only we never break one when we assume all the particles are clay. We never break a concentration of 1 microgram per liter. Here are the same results from the sensitivity analysis on settling velocities. It's just displayed in a slightly different way. And the takeaway here is that in the most severe settling case, we have 46% of arsenic mass being lost due to settling, whereas in the least severe case, we have only 2% of arsenic mass settling to the river bottom. Moving on to the groundwater model, one of the first things I did was attempt to calculate the initial groundwater concentration, so the concentration just under the the pits that store the fly ash. And so I used the summer models to do this, but there was a few parameters that were needed to be inputted. And so one of them was the concentration of arsenic in the recharge. And I calculated this with the equation shown on the top by dividing the concentration of arsenic in the fly ash by the Kd value. And we were provided a range of concentrations of arsenic in fly ash in the project guidance documents. I used the higher value to be more conservative, and through our literature review, our site-specific literature review in Module 8, we were able to identify a range of Kd values, and I used a value of 3.3 milliliters per gram. Another parameter that I needed to input into this model was the width of the flow zone. And so I went to Google Maps and measured the width perpendicular to flow for each pit. And then the two remaining parameters needed were hydraulic conductivity and head gradient, and those were obtained from literature reviews in Module 8. And all of this allowed me to use the summer model to calculate the initial concentration in groundwater. I opted to use the average of the multiple tracer studies that were performed to calibrate my linear velocity to 0.6 feet per day. And you can see the linear velocity equation that I used on the right. And I was able to keep my porosity the same at 0.025, uh, but I had to significantly reduce my hydraulic conductivity. So after calibrating the linear velocity, I was able to use the Domenico model to calibrate for the concentration at the farm well. Uh, and so you'll see this first Domenico screenshot on the top. My source concentration ended up being around 16.5 milligrams per liter of arsenic. Uh, when I used Google Maps, the distance that I measured from site C to uh, the Potomac was 2,100 feet around. And so I used that to calculate my dispersivities. There's no reaction, so lambda is 0. The source width is a perpendicular width that I measured in Google Maps. The thickness was given to us. The hydraulic conductivity came from my linear calibration. The hydraulic gradient was measured at site, both in between the Potomac and the pits and at the pits, and I took the value in between the two. Uh, the porosity uh, is within the range, as well as the soil bulk density and the KD, which is the KOC times the organic carbon. And so I was able to get a value of 0.65 milligrams per liter at the farm well. And when I calculated the total distance to the Potomac River, I came up with a value of 0 milligrams per liter. For site B, I was unsuccessful in my attempt to calibrate the model to the farm well, and I haven't been able to identify my source or sources of error. I adjusted my source concentration in accordance with what the Summers model outputted. I adjusted the dispersivities to account for the fact that Site B is further away from the Potomac River. I changed the source width and I adjusted the time to 6 years rather than 31 years. And my suspicion is that has a role in my inability to calibrate it successfully, but that was given to us, so there must be something that I'm doing incorrectly. Uh, but anyways, at the farm well, I'm getting a concentration of 0, and so I'm certainly getting a concentration of 0 closer to the Potomac for Site B. In conclusion, arsenic concentrations at the various water intakes are less than or equal to 10% of the 10 microgram per liter MCL. The contributions of arsenic from air deposition and groundwater migration don't appear to be significant enough to result in a surface water MCL exceedance or to even bridge the gap and get close to the MCL. For these reasons, I don't recommend proceeding with phase 2.